So welcome everyone to the last mathematical talk today. It's a great pleasure and honor to introduce Tamar Ziegler, winner of the Erdos Prize 2011 and European Mathematical Society Lecturer of the Year in 2013. Tamar is a professor at the Hebrew University of Jerusalem and is one of the leading practitioners in the rich territory that has emerged over the last decade or two that sits between ergodic theory, infinite combinatorics, number theory, and it's seen some spectacular results, some of which we'll hear about shortly. It's sort of a revisiting of an area that was, to some extent, founded by Hillel Furstenberg, who I'm sure would enjoy what we're about to hear. She will speak to us on dynamics, arithmetic progressions, and approximate cohomology.
Did I do this right? Okay. So thanks for the introduction. Tom promised me a tap dance. Okay. So it's a great pleasure to be here. It's my first time in Oxford. Okay. So let me start with I like to start with a motivating example. So a motivating problem. So here's the problem I want to consider. So suppose you start with an infinite abelian group G, and you have an infinite dimensional vector space over some field K, and you have a map from G to the endomorphism group of V. So these are just linear maps from V to V. That is an almost homomorphism. So what do I mean by an almost homomorphism? I look at rho of x plus y minus rho of x minus rho of y, and this is the rank of this map is always bounded by some number r for all x and y. So take 1, for example. So for all xy, rho x plus y minus rho of x minus rho of y is smaller than 17. Okay, and so the rank is just, so a rank of a linear map is like, okay, it just means that the image is trapped inside some dimension r vector space. And the question we want to ask is the following. So the question is rho close in the same measure? Is it close to a true, honest-to-God homomorphism? So what do I mean by that? So can I find a homomorphism such that the rank, for all x in G, the rank of rho of x minus sigma of x, so sigma is a homomorphism, is bounded by some number that is, well, it can depend on the group, definitely can depend on the group and on the field, but definitely depends on R. Okay, so something that depends on R. So maybe 56. Okay. Okay. Anyway, so and I want to use this. I want to use this question as a window to describe to you developments in recent developments in ergodic theory and additive combinatorics. And try to cover all the topics that were in the title of my talk. So here's a good place to start, as with arithmetic progressions. Arithmetic progressions in subsets of integers, or maybe one should call it the indestructibility of arithmetic progressions. And so here's the following. Here's the question. You have some subset of the integers that is of positive density, so say take some positive proportion of large intervals, of growing intervals. And there is a theorem by Roth in 1952 that states that any such subset would contain a 3-term arithmetic progression, so 3 points that are equidistanced. And actually, as result is stronger, it's not only positive density, but asymptotic density, 1 over log n. So if you look at a set for n large enough, if you look at a subset of the interval 1 to n of density 1 over log n, then you would find, you'd certainly find a 3-term progression. So this is the indestructibility of 3-term progressions. And then Semeredi generalized this to the indestructibility of any k-term progression. So if you take a sufficiently large subset of the integers, so if you take a positive density subset of the integers that it contains, certainly will contain k-term arithmetic progressions, and And the third one in this historical context, the third result I want to talk about is theorem of Gowers from 1995, where he manages to generalize the argument of Roth and obtain a Roth-type result, asymptotic density of 1 over log n to some power. And it's these ideas that came in the work of Gowers that I will start my talk. I will focus on first. So, okay. So this I want to I'll come back and go away from the integers, but I want to talk easier to explain, and also in the context of the question I started with. I want to work instead of in the integers. I want to work on a vector space over some finite field K. Okay, so K is some fixed finite field, and I'm looking at an n-dimensional vector space. And the way you should think, I fix this n-dimensional vector space, but in your mind you should have a family of vector spaces that grow in size, and all results are true for n that is sufficiently large, which is independent of all other. So all the constants, everything that comes up is independent of n. It's true for n sufficiently large. And so the Roth argument was adapted by Meshulam to this context. And so I want to show you the argument. So I'll call it the Roth-Meshulam argument, and it says that E contains a three-term progression. So what is the idea behind the argument? It's the following. Well, it could be that your set is what you call Fourier uniform. All its Fourier coefficients are small, and if your Fourier coefficients are all small, then your set will have the same number of three-term progressions as a random set of the same density. So what do I mean by that? If you flip a coin at any point in your vector space and ask whether it's in E or not, how many three-term progressions you're trying to solve? Okay, so you can think of it. I'm trying to solve this equation, x plus y equals 2z inside my set E, and I'm trying to count how many solutions. And if my set were random in this form, I would expect to get delta cubed times the size of v squared solutions, right? So delta for every flip, and the number of the count would be something like would be v squared. So this could happen, and then I'm very lucky because I find lots of three-term progressions. And if that doesn't happen, then the characteristic set of E, so E has a large non-trivial Fourier coefficient, and that can be translated to that E has increased density, larger density on some affine hyperplane. So I want to pause I want you to get a good feel for this. So for example, if your set was a hyperplane, or if your set was a hyperplane, then certainly you expect to get more three-term progressions, right? Because if 2 points are inside, then automatically the third point is inside. And similarly, if your set were trapped inside some hyperplane, then this would also happen, right? So you would expect to get more three-term progressions, because now you're relative to this, you're in the same set, but relative to this hyperplane. But the beauty of this is that, well, these are really nice cases, but in general, your set is scattered all around, and you have no clue what it looks like. But Fourier analysis allows you to pick out this if you don't have the right. So if you don't have the right count of solutions to this equation, really what this means is that you're concentrated. There is a hyperplane where your set is more concentrated. There is some accumulation of points on some hyperplane. Okay, so this is the way one wants to think about this argument, and Fourier analysis picks up this hyperplane for you. If you use discrete Fourier analysis, this would pick out this hyperplane for you. But I want to just remark this, because this is kind of a side note to my talk. But if you focus on K equals F3, then this is a very well-known problem. It was known as the cap set problem. And it was conjectured that actually a set that is three-term progression free should be of exponentially small density. And this was proved just maybe a year ago, maybe a year and a half ago. This is a recent development was proved by Ellenberg and I don't know how to pronounce this name. Some name. Sorry, I don't want to mispronounce it. And but it was following. So they proved it. They proved it in this case for F3, but it was following a breakthrough by Colt, Levin, Pach, who proved this result for the field with 4 elements. So, but this argument that they have. So maybe I should say. So the argument of Roth and Meshulam gives you a density of 1/n, and this. So 1/log the size of your set. And but this argument as the moment doesn't scale, and I want to talk about longer progressions. So this is just a side note. It's very, very new, exciting development, and maybe great things would come from their approach for this for the longer progressions. But at the moment, we don't know. Okay. So what about 4-term progressions? So what happens if you try to understand 4-term progressions? So the first thing you might notice is that Fourier analysis is not sufficient. And the reason is, so here's a reason is the following. So here's an example. So suppose you have a quadratic form. So I say high rank, so think of it as this is your quadratic form, and high rank would be that this matrix has high rank as matrix. And if you have a high rank quadratic form, and you look at the variety defined by it, so you look at E is the set of x of the zeros of this quadratic form, then you can check that all non-trivial Fourier coefficients are small, but E has many more 4-term, well, also 3-term, but 4-term progressions than expected. Actually, not 3-term. That was wrong what I say. Well, if it had more 3-term progressions than expected, then it would have. You should have immediately shouted that it would have had a large Fourier coefficient. I would have picked it up before, but it doesn't have. That doesn't happen. So, but there's this other algebraic relation that holds among 4-term progressions. So this is this q of x minus 3 times qx plus d. Well, it's written out there, and this equation. Tells you that if you have 3 of these points on this quadratic surface, then automatically the 4th one in. So your count of points of 4-term progressions is biased. Okay, and okay. So and the beautiful thing is that that actually this is a result of Gowers green tau. So some large portion of the argument sits in Gowers' paper, and there's a very beautiful twist at the end that allows one to actually pick up this quadratic form and says the following. So I already told you kind of what's going to happen. So how can I prove that E contains 4-term progressions? I can try to do this kind of follow this philosophy. Either my set is quadratically uniform, so all my quadratic Fourier coefficients are small, so I include the linear ones as well. So either all my degree smaller than 2 Fourier coefficients are small, whatever this means. I didn't write that in well, maybe I'll write that later. Or, and in which case E has the number of 4-term progressions as one would expect in a random set, so same as tossing a coin. And if this doesn't happen, if I have a bias, if I witness a bias in the number of 4-term progressions, then the reason for that is really the previous slide. The reason for that is they sort of accumulate on a quadratic surface. Or E has a large quadratic Fourier coefficient, which implies that E has increased density on some quadratic surface. Okay, so Fourier analysis doesn't pick this up, and into this theorem goes a lot of additive combinatorics, and so it's much more difficult than the previous one. Is to show that if you're not well, never mind. Let me stop there. Let me just say that this raises. Okay, so this raises the following question. So suppose you are trying to count k-term progressions, and you're given that your count is biased. You have too many or too few. Your count of d-term progressions is biased. Then you can ask yourself, does this mean that that your set has an increased density on a degree d-1 subvariety? So is the reason to that that your set is not the entire set, but there is some concentration. If your entire set were concentrated on and maybe one surface, then typically I would expect that would be much easier to find. So, but the problem is that you could pick a few of these kind of that don't talk to each other and put a little extra of your set here and a little extra of your set here, and then the other points are kind of scattered. And then the question is, how do you pick out? So what would be, we would want something like Fourier analysis to pick out the quadratic d minus 1 dimensional surface that, should be, instead of you don't need subvariety of bounded codimension. You can have a hypersurface. So, okay. So here's a first observation by Gowers, that it's better to count, instead of counting progressions, it's better to count d-dimensional, or in this picture, 3-dimensional. Instead of counting 4-term progressions, it's better to count 3-dimensional cubes. And if you have a bias in the count of progressions, then you have a bias in the count of cubes. So this would be better for you to count. And cubes enjoy lots of symmetry, so that makes your life nicer in many cases. And this coupled with this observation that if you have a polynomial, so you can define a polynomial of degree smaller than d. P is a polynomial of degree smaller than d on V, if and only if it vanishes on all d-dimensional cubes. So maybe just an example. So you see that you're okay. So if I knew that it vanished, if I knew it had a polynomial and I knew that it vanished on all edges, so on all one-dimensional cubes, this would mean that f of x is equal to, well, vanish. I should say what vanishes is. Oh, I forgot about that. So vanishes means that if you count, if you look at an alternating sum of the function over the vertices of the cube. Okay, I didn't want to write down the formula, but basically this would mean that, so if I had an edge, this would mean that I'm looking at f of x minus f of x plus u. And if I know that, if I know that this is 0 for all x and u, this means that my function is constant. Okay, and similarly, if I would x plus v plus x plus u plus v. So this is x plus v, and this is x plus u plus v. So if I were to go around these vertices of the cube and count myself alternating, then a function is quadratic if is linear if and only if this condition is satisfied. There's this characteristic issue. So you can have more functions satisfying these conditions if the characteristics that vanish on cubes than just honest-to-God polynomials taking values in the field. But I don't want to get into that now. So we will always assume, if I forget to write in some place that we are assuming high characteristic, although we understand the story also in low characteristic, but there are various complications that come in the picture. So a polynomial. So if what would be my question then? So yeah, and this other remark: a degree smaller than d varieties have more d-dimensional cubes than expected, than what you'd have than a random set. So the question you try to ask yourself is the following. This was known as the inverse theorem for the Gowers norms over finite fields. Suppose you know that the number of, it's one of the formulations. So suppose you know that the number of, you have a bias in the number of d-dimensional cubes in some arbitrary set E. Well, this implies that your set has a bias, so your set is over-concentrated on some degree smaller than d hypersurface. Okay, so I want to leave this question alone for a bit and take you on a tour on the ergodic theoretic side. So here's a different story. So there is the Semradi's proof of the theorem of having sets of positive density in the integers having k-term progressions, and shortly after Semradi's theorem, Furstenberg came up with an ergodic theoretic approach to this problem, which follows the following. So it starts out with this following theme, which is now known as the Furstenberg correspondence principle. So suppose you have a subset of the integers, and it's of positive density, then you can associate to it a measure-preserving system. So this is a measure space, x b mu, and a measurable transformation from x to x, and that preserves the measure. So this is a morphism in the category of measure spaces, and a distinguished set A with positive measure. So I have a measure-preserving system, a distinguished set A. Well, this might not be so interesting, but I also have this condition that if I look, so here's this X, and here's the set A, and I look at my return times to the set A. If I have these positive intersection of return times, so if the intersection of mu of A and T minus N1A and so on is greater than 0, then this immediately implies that the original set E had the same recurrence phenomena, or same difference phenomena. And then he proved the following theorem, which is the multiple recurrence theorem, that here's the case. If I fix n1 to nk to be n through kn, then to say that one of these elements in this sum is positive ensures that I have a k-term progression, maybe k plus 1 term progression, k plus 1 term return times to the set A, and therefore a k plus 1 term progression inside my set E. Okay, so you can ask yourself, okay, I started with an arbitrary subset of the integers, and but then I'm turned this question to an arbitrary set of positive measure. So why am I better off? And the reason you might be better off is that you could try to employ structure theorems of measure, or general structure theorems of measure-preserving systems to try to obtain, which is what Furstenberg did to obtain this result. So this implies Semirates' theorem. And his idea is to study these multiple recurrence or recurrence properties of your system via morphisms to simpler measure-preserving systems. So let me describe to you how Roth's argument looks from the ergodic perspective. The same, what is the philosophy there? It's very close philosophy. You can also see how some advantages of their ergodic approach. So here we have a measure-preserving system, x b mu t, and a set of positive measure, and a set of measure delta. And Furstenberg's proof of Roth theorem would say that there exists an n so that this intersection, the intersection between mu of, the measure of the intersection of A, t minus na, t minus 2na is greater than 0. So what is the strategy? Well, it's similar in nature. Well, either it could be that x has no non-trivial eigenfunction. There's no, in this case, the system is called weak mixing. And in this case, these sets A and t minus na and t minus 2na become sort of asymptotically independent. And in the future, this average converges to mu of A cubed. So in this case, that's clearly you have an n for which this is true, and then you win. Okay, good. If this doesn't happen, then you do have a non-trivial eigenfunction. So you have some function psi satisfying psi of tx is lambda psi x. So you can think of this in your mind. This should be the corresponding thing to Fourier analysis. So an eigenfunction, and what you can do is if you have a non-trivial eigenfunction, then this automatically gives you a morphism to a rotation system. So you have on top, you have the map between x to x. That's the original t, and then you have this. You can normalize your eigenfunctions. So a normalized eigenfunction, so it could be normalized to take norm 1, would induce a map to the unit circle, and then to say that it's an eigenfunction exactly says that on the bottom system, on the unit circle, your system is just, while upstairs I'm moving by t, downstairs I'm simply rotating by lambda. Okay, so I had this system x that I had absolutely no idea about, if I don't find any progressions in the, like lots of them in this sense, or if I don't have this random behavior, then that tells me that I have a non-trivial map to a circle rotation system, and I can, if I'm in the ergodic world, I can collect all of them. So I can look at all all my eigenfunctions and collect all of them, and this gives me a new system. So I look at the image of my x under all these maps. This gives me a new system. And in this system is what we call a Kronecker system. So it's a compact abelian group with Haar measure. And and downstairs in this system, my transformation moves by rotation. Okay? So, well, okay, I didn't tell you how I can deduce Ross' theorem for this, but here's this thing, some facts about this Kronecker system. So the first thing is it's universal, so it's the biggest such system. So if you have any other Kronecker system and a map from x to y, then this system would, any map to that system would factor through this Kronecker system. But more importantly, if I try to calculate this average that I tried before, so I tried to look at this. This was the average that I was concerned with. I just wanted 1n, but 1n is very difficult to find. So instead of finding one, I try to find many of them. This would be the same. I want to calculate this average. This would be the same as pushing the entire question down into this nice and simple, relatively simple dynamical system. So the relatively simple system downstairs, in your mind it can just be a circle, okay? A circle rotation. So downstairs you have a circle and you have rotation by lambda, and you have a map from, if you want to understand this average upstairs, the asymptotic behavior, then really you can push the entire question downstairs and calculate the average downstairs. So here's how this looks. So I want to calculate, so I have this map pi from x to the Kronecker factor, this abelian group with rotation. And if I want to understand this average up here, then really I need to understand this type of average in a much simpler system downstairs. So I push the entire question downstairs and I ask this, can you tell me that if I have, well, before I had a set, so before f might have been the characteristic function of the set A. But you can replace the set A with any positive function with positive integral and ask the same question, and then pi star A, which is what I wrote before, by pi star f would make sense. And then what I have now is this question. I have a positive function on a circle system, and I ask, is it true that this average over here is always positive? And that's very easy to see because n alpha returns close to 0. Well, I think of f as being, you can approximate it by a continuous function, and then this thing would be, n alpha would be close to 0 many times. Okay, when n alpha is close to your 0 element in your set, then n alpha and 2n alpha, and then you get lots of, then it's easy to show that this other average is positive. Okay, so you can try to, keeping in mind, so we know what comes for Fourier analysis for the Roth problem, and now we're interested in this finding some quadratic structure. Yeah?
What does pi star f mean?
Well, it's the push forward. You can think of it, if you want, as the projection onto the, if you work, you can think of the L2s if you want. That would be the easiest. Then you would think of the orthogonal projection on L2 of y, which would, L2 of z of x, which is a subspace of L2 of x. Okay, or conditional expectation would maybe, I don't know, whichever would make it easier. That maybe projection would make it. Anyway. Okay. So this is like an ordinary thing to do. Instead of working with sets, which are usually very robust somehow, it's much easier to work with functions, and all the properties are sort of the same. Okay. So keeping this in mind, you kind of think of what I want, what do I expect, what do I want to happen in my, if I'm thinking in my mind, I had this quadratic surface that I want to pick up somehow. So what do I want to have in these dynamical systems? So I have this eigenfunction, which for me is like, I want to think of it as like a linear function, so I need some replacement for polynomials. So what can I define as polynomials in dynamical systems? So if I have some group G and I have a measure-preserving system, so I want to think now, before I had the group of integers, but in my mind I'm thinking about this vector space. So I don't want to think of the integers, I want to think of maybe an infinite dimensional vector space acting on this measure-preserving system, but I can make this definition always. So I have this collection of, so I have a G action on X, so I have this collection of measure-preserving transformations, and I'm assuming, okay, I wrote ergodic, I'll maybe say, I'll get to that in a minute. So I can, ergodic doesn't make sense here, so you can just delete that, and I'll get back to that in a second. So suppose you have a function f from x to the complex numbers. You can sort of define what its derivative would be. So you can derivative in direction u in your group. So you'd look at f of tux times f of x bar. And you would say that a polynomial, p is a polynomial in your dynamical system of degree smaller than d. If you successively differentiate many times, you get one for all directions u1 through ud for almost every x. Okay? So here are examples. If you knew, if you knew that that the derivative of f is 1 always, then well, if you plug in u equals 0, you find that f takes absolute the absolute value of f is 1, and saying that for any other u, you would get that f of tux is equal to f of x, and to say that this implies that your function is constant is the assumption of ergodicity. So we assume that. Okay, so my beginning is constant functions, and constant functions are the ones that satisfy that their derivative is trivial. Okay, so it's a kind of a multiplicative derivative. It's not an additive one. And the second observation, so in the same way, so an eigenfunction would be a degree smaller than 2 polynomial. Differentiate. If you have an eigenfunction, you apply this process twice, you trivialize. So, okay. So here is an observation which could have been actually made before. Is also in polynomials in just any group, is that to say that a function is a polynomial is, well, I said it actually, okay? It's the same as saying that it's that it's alternating product. So in this case, my minus is just conjugate. So, and my alternating product is 1 on the vertices of the cube. Okay, so if I want to understand polynomials in dynamical systems, are those who would vanish on dynamical cubes. Okay, so now you can guess what we want to have. So we have we have a group G. So say our group G is an infinite dimensional vector space over Fp. This is my G system, and I want to remember we're trying to count. I told you that progressions may be not such a good thing to count, so we can try to count or easier to count cubes. So we're trying to count cubes. So this is a count of 3-dimensional cubes, or some way of thinking of not counting. So this is, I'm checking out the intersection in times that belong to a 3-dimensional cube in my dynamical system. And this is something that I would want to understand, this in correspondence to trying to understand the number of cubes in a subset E. And the theorem that we can prove is in joint work with Bergelsen and Tau, is that there exists a polynomial system, like I can collect all these polynomials, like I collected all these eigenfunctions, and compose out of them a system. I call this a polynomial system. So it would certainly be much simpler than just a general dynamical system, and with the same property that I had before. So it's the smallest, it's the largest such polynomial system, and with this property that if I try to evaluate the d-dimensional, so fix d equals 3. Okay, so if I try to calculate, so over here I have there is a v here that doesn't have to be there. Anyway, so on this E over here denotes some averaging scheme. So this is an infinite group, so I need to take some large subset that grow into the group. So I have some averaging scheme. And if I take this averaging scheme and I measure it upstairs, then that would be the same as pushing it forward to this polynomial dynamical system and evaluating the average downstairs. Okay? So this is the concept you should keep in mind. I have a complicated system. I have no idea what to say about it. But if I'm just interested in this question of progressions, then there is this underlying structure that I can try to pick up. Like before, I picked up for the Roth question, I picked up the structure of an abelian, a factor system that is an abelian group. And here I pick up a factor system that is made out of the polynomials in the system. So what does this thing look like? So here is just you should have the same picture in your mind. So if I'm going over some averaging scheme and I'm trying to find out what the average over cubes upstairs is, can push the cubes down to my dynamical, to this nicer system. So this is a cheating system because it's no longer a circle rotation downstairs. So it's no longer the system downstairs. If it were a circle rotation, it would be the same as then Fourier analysis would suffice for this problem. So it's kind of cheating. I'm not very proficient at making these diagrams. So it's not a circle rotation. But say in the case of maybe I should say something about what the content of this is, or what in the case of d equals 3, this is what would correspond to the quadratic case. So in the quadratic case, the system downstairs would look of something of this type. So you would have this z of x, you would have this Kronecker factor. So this is an insufficient factor. It's an insufficient place to check out what happens to your average, but you'd have some extension of this, so there would be some. So this is what the Furstenberg argument, and in this case, Zimmer, would tell you that in the case d equals 3, you can reduce to a somewhat structured set. So what does your system look like? It looks like a product of your Kronecker factor, your abelian group, with some other metric space M, and your transformations, your group action. So TV takes xm to well, this would be x plus some alpha v. Okay, so this is over here. I have rotation. This is abelian. Everything looks great, and on the other part, I have rho v of m, where this is some isometry acting on this m. Okay? Sorry. Yeah. And the name of the game, or in order to, so this kind of structure is kind of sufficient to get this lower this lower limit to get some. It's sufficient structure to get something to give you positivity. But if you actually want to classify exactly what should be here, then the name, so sort of the difficulty is to try to get structure on this cocycle extension rho. Try to use the fact that somehow it's not equidistributed over what happens below to try to get some algebraic structure on this cocycle extension. But this is like it's on one foot. It's an explanation. It's not a true explanation. But this is what goes on in this. So now one can use a version of the correspondence principle that I described at the beginning, the Furstenberg correspondence principle. Can use a more complicated version of that to export this result to the original question I asked. So the original, no, maybe not original, like the second question. The second question I asked, which was about n-dimensional vector spaces. So I have an n-dimensional vector space. So this is now the inverse theorem for the Gowers norms over finite fields. And it states the following. So I'm reminding you what the question was. So if I have a bias in the count, if I have this non-random behavior in the count of d-dimensional cubes, so counting, okay, never mind. In counting t-dimensional cubes, then E has increased density on a degree d smaller than d hypersurface. So you can use that to kind of pick out this nonlinear behavior in the set E. And of course, all the bounds depend on delta and k. So here's an alternative formulation of this. So alternative formulation would be that if my count of cubes is incorrect, so I wrote it on the slide, but I think I didn't mention it. The expression that counts the number of cubes is what is known as the Gowers norms. So if my Gowers norms is if my number of cubes is incorrect, I have a bias in the number of cubes, then there is a non-trivial degree smaller than d Fourier coefficient. So if this were linear, this would just be a regular Fourier coefficient. So this is a degree smaller than d Fourier coefficient, and with some bound depending on the field k and delta. And one of the, I guess, major questions in additive combinatorics would be to give to give bounds on this on the C of delta and k in terms of delta and in terms of the field k. So now the only proof we have goes through this detour through this ergodic theoretic theorem and gives absolutely no bounds, except in the case d equals 4, where we have in d equals 3, which d equals in the quadratic case that I described in the Green-Tau-Gowers theorem, where we use the tools from additive combinatorics. And over there, we can, using those tools, one can actually get, this is also quite recent, the best bounds come from a result of Tom Sanders that gives C. So what you would want is to have the bounds to be of the form delta to some constant depending on k. And what you can get from Sanders' result is something like 1 over q to the power of 1 over log delta to some power or something like that. So this is known nowadays as the quasi-polynomial Feynman-Ruzha conjecture, or Feynman-Ruzha quasi-polynomial Feynman-Ruzha theorem, which is the theorem of Sanders. And the conjecture would be to get this bound over here. Okay, so good. So I don't have much time, but I'll try. Okay, so I said the main open question is this dependence on these constants. Maybe it would be very difficult to get this constant to be polynomial, but as a first step, you might try to just get rid of the dependence on the field, and even that we can't do, or understand the dependence on the field. At the moment, we have no understanding of the dependence. Okay, so I'm back to the original question. So this is the true original question, so the one I asked at the beginning. So I have this vector space, infinite dimensional vector space over finite field k. Well, I'm going to fix this finite field k. So you can ask this question over any field. And I want to fix the group G to be also a vector space over k. And here's the question. So I have a map from this vector space over infinite dimensional vector space to the endomorphism group over k of this of another vector space. And I'm giving this condition that the rank, it's a homomorphism up to this bounded up to rank R. And I want to show why there is a homomorphism. I want to show you how you can find a homomorphism so that using this kind of nonlinear or higher order Fourier analysis, how I can show you that how we can pick out a homomorphism to fix this question. So here's an argument. So this argument, I'll describe you this argument that David Kashdan and I have, but it's based mainly on ideas of Green and Tau and Shachar Lovett, who when they proved the equivalence between the inverse theorem for the Gowers norms and in the Freiman-Ruger conjecture in the case of degree 2 polynomials. So I'm guessing this argument is most likely known to them, but we couldn't find it written anywhere. So let me describe you what the argument would be. So first you try to approximate this problem with some finite problem. So here's you say your W and V are both finite dimensional subspaces over K, and K in this case is Fp. And you look at the following function. So you look at this function on W squared, W cross W to the field, which is defined as f of Wx is EP, so I should write, I already wrote that in the previous day. So EP is just, EP of x is just e to the 2 pi I x over p. Okay, so I look at this function, and why do I expect to get something good out of it? Well, if I fix W, this is a quadratic form. So already I have some quadratic behavior. That's true polynomial behavior. That's very encouraging. But but this rho is, well, it's not, if it were truly linear, if rho were truly linear in W, this would just be a cubic polynomial in W and V. If rho were to satisfy the condition that rho of V plus W minus rho V minus rho W, if this was a zero, a true homomorphism, then this would be a cubic polynomial in X and W. Okay, if you differentiate it 3 times in X and W, this expression would annihilate. But it's not. Okay, so I can't expect this to be a true polynomial, but I can expect maybe to pick up some bias in my, so I said that we expect it to behave somewhat like a cubic polynomial. I expect is kind of a cheating. Why? It's not exactly expect, but if it were truly linear, then it would be a true degree 3 polynomial. And I know that degree 3 polynomials annihilate completely when vanish on 3-dimensional cubes. So maybe I can try to pick out some bias on 3-dimensional cubes using the fact that that I'm bounded rank. And to our aid comes a classical result from about quadratic forms. So if you have a quadratic form and you look at the exponential sum, then the higher the rank, the more equidistributed it is. So a low rank quadratic form is biased. Okay, there's a bias in the exponential sum, and we're given that this creature, this rho of u plus w minus rho of u minus rho of w, this guy is a bounded rank. So we can try to use it to pick up some bias in the count of 3-dimensional cubes, and indeed you can do that. Okay, so you can conclude, I wrote conclude, but you can, if you work some algebra, it's like 3 lines, then you can deduce that that you have a biased count of 4-dimensional cubes. Did I say 3 all the time? So, okay, you have to forgive me because it's very difficult to keep track with the numbers. So 3-dimensional cubes correspond to quadratic polynomials. So if I want to get something cubic, well, if it were truly linear, it would be cubic, then I should try to go for 4th-dimensional cubes and not 3-dimensional cubes. Okay, so did I write that? I don't know if I wrote that wrong before, but it says 4-dimensional. I think I caught this a few days ago. I did write 3 at the beginning, but now it's 4, so I hope it was 4 before. So I'm trying to pick up, if it were truly linear, if it were truly a homomorphism that would be truly cubic, then it would be, it would have it would have exactly the right number of count of 4-dimensional cubes, and in this case, I'm hoping to pick up some bias. So again, you might protest that this is not a set and this is a function, but you can do the same manipulations with functions instead of with sets. So I'm trying to pick up bias in the count of 4-dimensional cubes, and the theorem that I mentioned before, the inverse theorem for the Gauss norm over finite fields gives you a candidate for who this cubic polynomial might be. It gives you a candidate for a truly algebraic structure that is related to your problem. So there exists a true cubic function, but it's cubic in these two variables, w and x. And your function, this is the function we were looking for, it correlates with that. If I have a bias on the number of four-dimensional cubes, I have a cubic Fourier coefficient. Okay? So you need to work a little harder. It's an oversimplification, but basically, if you look at this cubic function, and you can see that it's going to be quadratic, and well, you can show that it has quadratic behavior in x and linear behavior in w, and this would be your quadratic approximation to your rho. So this is kind of the general theme, together with David Kashtan, we were trying to think about this problem because we are interested in a different proof for the inverse theorem for the Gauss norms. And so in the course of it, we came up with this question, and then kind of a general framework to try to understand these questions. So this is this notion of approximate cohomology, and maybe it exists in some other form, but we couldn't find in some other place in the literature. So let me just quickly describe it and then finish. So you have some abelian group and a G action on this group, and this abelian group M comes with a filtration. So a filtration is not subgroups, but just a bunch of increasing subsets, okay, that the action of G preserves, and it satisfies this condition that if I add the two subsets that it's contained in some of the so it shouldn't be this is a misleading thing. This is just sets. It's not a subgroup. MI are just arbitrary sets. Okay, so I'll give an example in a second, but let me just say, so you have this filtration, and you can define the notion of an approximate cocycle so as follows. So you have a cochain from GM to M, and you'd say that it's an approximate cocycle if the image of the boundary map is inside this one of these sets MI for all, okay, the image I just said. So it's in some fixed I. Okay, and similarly, you can define the notion of approximate coboundaries and then approximate cohomology groups. So here's one example of the example I described was you would look at M to be the group of endomorphism of a vector space V, and you would look at the rank filtration. So this would satisfy this property that the property over here. And if you look at the trivial action, then what a true cocycle is a homomorphism, and this question is just asking whether a true approximate one cocycle is close to a true cocycle. So you can do the same thing. So here's another example of some filtrations you can take. So you can take in general, you can take the set of all degree D polynomials. So fix a D, look at degree D polynomials on your subspace W, and you can define the notion of rank. So we call this algebraic rank, but then Trevor told me that this is actually called the H invariant. So Schmidt H invariant. So you can define a notion of rank on degree D polynomials by the minimal representation as a sum of a product of two polynomials of lower degree but not trivial, so not constant. So this would be if you think about it, if for example a quadratic this exactly would be the same of what you have in mind when you have a quadratic polynomial. So a quadratic polynomial would be of rank R if you can write it as a sum of R products of linear polynomials. Okay, so this is a generalization of this notion of rank, and with this notion we can prove the theorems. So if you have a true cocycle, then its image or a true coboundary the same, then the image is always an approximate cocycle or approximate coboundary. So you have a natural map from H for the true H cohomology groups to the approximate cohomology groups, and we show that this map is onto. So if I have any almost homomorphism into this polynomial, into polynomials with this filtration of bounded rank, then it's close to a true homomorphism. But just to show you the extent of our unknowledge is that we don't know anything else. Like we don't know what to say if, for example, if the field is K. We don't know what to say if the group is Z, and even, well, we can do 1 if rank 1, like if R was 1, the original question with 1, but 2 already is complicated. So, so this is, so we know very little, but we can actually calculate the kernel of this map as well. But we know very little, and there's lots of very interesting questions there. So I'll just finish by saying that you can use the toolbox of additive combinatorics to recover the inverse theorem for the Gauer's norms over finite fields from this theorem over here. So this is our somehow initial motivation for this is to try to get some outside intuition on or maybe some on this question. So I'll finish here.
Thank you very much. Are there any very brisk questions or comments? Tim.
This point towards a strategy for H2.
For what?
Same question with H2.
I have no idea. I think it's a great question, but I don't know how to solve it. Yeah, so.
Yeah.
I think you more or less told that it was difficult, but can you give the structure of the system, the ZD of X, these characteristic factors?
Well, I said something over here. So, for example, in the case D equals 3, well, for
the cocycle has to be continuous or something?
it has to be, no, in this case it would have to be linear. So for any fixed V, it would have to be a linear map. In the sense that, well, you can, I didn't write it. So you can actually show that, first reduction, you can show that this thing actually takes value in an abelian group H. And then it would be a linear function on this, in the sense that I described before, of this cocycle would take values in the linear functions on this. So, and then this whole thing would be a quadratic creature, the extension. So in your mind, you should think of for Z action, that would be more easier to think about. So this system that would come out for this next case after Fourier analysis would be a system of this form. Okay, so this system supports degree 2 polynomials, and actually.
So it's a question that when you stop the group.
Well, if the group was Z, then there's a big story, right? The story is different, and it's insufficient to look at these polynomials. You need to look at these nil manifolds. And if life were easier in the Z action case, then this is what you would hope to. This is what you hope to get, but it's not the truth. So, but the corresponding system that comes up here in the Z case would be a system of this form. So the intuition for you should come from here, and in the finite field case, a bracket polynomial is a true polynomial. So there's no this nil behavior is truly polynomial. You can just put this thing in a nil system for the direct sum FP action. You can do that, but secretly you will think of it as a nil system, but actually you can describe it as this kind of polynomial system. So there are true polynomials there, and nil systems they don't support. Well, in general, don't for Z nil systems they don't support, like the Heisenberg one doesn't support true polynomials of degree greater than 1.
Okay, thank you. Before we hand over to Nick, let's thank the speaker again.